Okay. Good afternoon, everyone. You guys having a good day? Day one or day three, depending on how long you've been here, or how long it feels, depending on how light you were out last night. So my name is Grant McAllister. I'm a senior principal engineer. I do work on the stuff, not a marketing guy, so I should be able to answer most of your questions. We're going to be talking about RDS Postgres today. I'm going to go over some of the new things that were either released in the last year or coming up here shortly. And then I'm going to spend a bunch of time really talking about the things that we've learned working with the customers over the last 2 years on Postgres and specifically with RDS. And really some of the best practices, some of the tips that'll help if you're using RDS, help you make your experience that much better. So let's jump right in. So, there we go. One of the first things that customers have been asking us for quite a while is major version upgrade. I'm happy to say it's coming out really soon. Post-reinvent here should be out really soon. And it's really simple to use. You basically select a new version, you hit the button, modify now, and you get started. So you start with your production 9.3 instance. We take a backup right away because we want to make sure you can always get back to a safe state. Then the next thing we do is essentially we're running PG upgrades. So any of you guys that have been running Postgres for a long time, you know what PG upgrade does. This will take about 5 minutes on a typical database, but it is dependent about some of your size and how many objects you have in it. And then, of course, what we do is we take a backup before we give it back to you, because guess what? PG upgrade is not transactional, right? There is no transactionality. During that time when it's moving stuff around, you can't recover to it. So we want to make sure we had backups on both sides. So you end up with a 9.4 database. You're all good. One of the things that you have to know is that during that time, because there's no transactions, you can't ask RDS to restore to it. So we make a thing called a blackout window that just says, hey, you can go earlier, later, you can pick one of those backups, you just can't go in the middle. Now, this is how simple it is, but of course, the best practice, of course, is not to do this. It's to go and make a test copy of your database, go run the upgrade, get your test 9.4 instance, get your application and test it, right? When everything's good, then you want to go and do the real one. And this is because, there are a few things that PG upgrade will kind of have a problem with. Open prepared transactions. Now we check for a bunch of these, but it's impossible to kind of do all of them. And it's also impossible for us to verify that the functionality of your application wasn't dependent upon some quirk in, let's say, 9.3. So that's why you really want to do that testing. But once you've tested, it's a real simple process to do. So as I said, this will be coming out very shortly. Some other new stuff that we've done. We introduced larger storage. So before we had 3 terabytes, we now go to 6 terabytes. So we increased that size, doubled it. The IOPS maximum is still 30,000, right? So that hasn't changed. That's mostly based on the instance classes, about throughput of IOs. But the nice thing is GP2, because you get 3 IOs per gigabyte what you buy, now that you can buy more, you can get more IOPS and more throughput. So it will depend on how big you go, but typically we've seen good customers get good increases on that. One of the big ones that I was really excited about was encryption at rest. We have this across the whole RDS line, but for Postgres especially, it was real good because a lot of people are trying to get into more compliance-related scenarios with Postgres. So this includes all your data files, your log files on the machine, all your backups are encrypted, and your logs that we ship to S3 for your backups for point in time. Now, we use our Identity and Access Management Key Management Service, KMS, is the thing that manages the keys. So we don't manage them for you, they're your keys. Now you get a default key that you can use. I recommend using a custom key per database. This over time, as we get more rich features around this encryption, you'll want to have a separate key for each of your databases because you won't want to have to grant access to keys if it's just one big default for all your databases. So that's just kind of the best practice there. Now, one of the things that people asked me as soon as I told them we have encryption at rest was, what's the overhead like? I really like the idea of encrypting my data, but should I do it? So what I did was I ran PG bench, read only, in memory, right? Now you'd expect no real overhead. I have transactions per second on the vertical, and then just increase the number of threads along the bottom. So the green is regular, the blue is encrypted. And what you see is there's basically no difference because you wouldn't expect it, right? We're not touching the storage. So exactly. What about read-write? We're doing a lot of reading, a lot of writing. We're actually going to see a bit of a change. So you'll notice here that as I start getting up into the 62, 32, 64 threads, I start to see a little bit of a difference. And when we measured, it's about 5 to 10%. Now, if those of you guys, how many people have run PG Bench a lot? 2? So it's fairly write intensive when it's actually in write mode. Like on this box, I think it was doing 2,000 or 3,000 IOPS writing and only about 1,000 reading. So it was still doing a lot of I/O that has to go through the encryption system. So you may actually see less of an impact depending on how much I/O your application's doing. But this one was actually doing a lot. We're always rolling out new versions. We had a bug in 9.3.5 in our code around our permissions for RDS super user, so we fixed that in the 9.3.6 version and all the subsequent ones around reset all. We released 9.3.9, that's the new default on 9.3. We released 9.4, that's been out for almost a year. Has a lot of great features that, like JSONB. What's really cool is we saw huge adoption on 9.4. So 9.3 was still our default. We released 9.4. Within 2 weeks, we were getting an equal number of creates on 9.4 as we were on 9.3. So the adoption's just been huge. Customers are just really loving that. So each one of these releases, we typically update like PLv8 and PostgreSQL. So if there's specific stuff you're looking for, we document that on the site. So 9.4.4 is our default overall on all our instances. So one of the ones I'm really excited about that we've had a lot of conversations with the customers is, they said, I love running RDS, it's really simple, it's really manageable, but I can't see the stuff that I want to see on my instance. I'm used to being able to go poke and prod and see all the statistics. So this is what we're coming out with. This is also going to come out really shortly after reInvent. It's basically enhanced operating system metrics. So I won't go through every one of these, but you can see things like CPU utilization, not just overall, but I can tell now system time, I can tell idle, I can tell, steals because it's in a virtualized system. But the one I'm most excited about is really the process list. This is giving you functionality like you would have with POP on Linux, right? You'll be able to see what's vacuum doing, how much memory is it consuming, how much CPU is it consuming. And this is historical, so it's at a 5-second granularity, and you'll be able to look at it over time, both on a console and through an API. So you can build your own dashboards if you want, or you can just use ours. And so ours is going to look like this, much like you see with all of our metrics. You'll be able to graph them. You'll be able to put alarms on them. So pretty much what we have, like what we have for our standard metrics, but just a lot more detail and a lot more frequent. And over time, we'll look at increasing probably the granularity and the statistics we give. But I think this is a really big move forward because if you have those spiky kind of things where somebody comes in and spikes your CPU for 20 seconds, today you'll just see your average go up. Now you'll actually be able to go and see exactly what happened and what's going on your system. So really key. So let's talk a little bit about what's going on with data movement. How many people heard in the keynote that we've got a nice little new tool? Good, good. So I'm not going to spend too much time on this because a lot of people probably heard about it, but I think this is huge. The database migration service is, it allows you to go basically from any of those engines. You can mine out of Oracle, Postgres, Aurora, MySQL, and you can go into them. So you can go MySQL to MySQL, you could go MySQL to Postgres, for example. You can go Oracle to Postgres. And that's really actually really nice because we get a lot of customers who are saying, I need to move data around. And this is a migration service, but it can also be used for replication. Come on. So there we go. So this is just the standard picture of showing, if you were on premise and you wanted to do a migration, you basically, you got a VPN into EC2 or an RDS instance. You basically ask for a migration service to be spun up, and that's the little cogs there. You go connect it. You say, hey, here's my URL for my source and targets, permissions. You go select which tables. You can say, hey, take all my tables, take just this one, whatever you want. And then you basically do a full data load. And this is going to do a select and basically, do that. So you need to be able to get a consistent select of your table. And then essentially, in the meantime, you're generating logs, right? And in the background, once the full load is done, we will catch up with the incrementals. And so we'll take all those logs, we'll mine them, we'll stream that over. Once you're all caught up, all you got to do is then switch over to here. So it won't be a zero downtime because you got to stop your application and start it, but it could be a few seconds for that outage. Now, what does this mean for Postgres? So today, you have to be on 9.4 for this to work because we're using the logical replication features built into 9.4. So nice thing is we support major version upgrade. You guys can upgrade your ones. The source today can only be EC2 or on-premise. We don't offer RDS at this point as a source, but just as a target. So as I said, it's bulk copy, and then it's change data capture. And if you're interested in that service, we have web pages up there you'll be able to find online to be able to go sign up for the preview, and we can get you started. So if you've got a migration or some replication that you'd like to do, this is really going to be huge. So one of the other things we get is a lot of questions about how's the best practices for loading data. So if I'm going to use this kind of tool or I'm going to do something myself, what do I want to do? So it's the normal rules of, hey, you want to make less work for the database. Turn off backups, which are, with our system, it's setting backup retention to 0. You want to turn off multi-AZ. You want to turn off auto vacuum. Now, of course, you got to remember to turn these back on or bad things are going to happen, right? But it really does make it much faster. If you're using, dump, you want to use compressed PG dump. Restore you can do in parallel. But of course, now we have a migration tool that you might be able to use instead of these. You want to increase your maintenance work memory. We leave this at 16 meg by default because we don't know what kind of size box and how much you want to give to it. So it's definitely one that will help with both index building as well as vacuuming. So you really want to show, and I'll show you some numbers on that. And then the other one is checkpoint segments and checkpoint timeout. So in Postgres, every time you modify a block, the first time you do it after a checkpoint, it has to log the whole block. So if you're checkpointing too frequently, you might double or triple the amount of wall generation that you have. So setting your checkpoint segments is really important for a lot of reasons, replication, but as well as data loading. And I'll show you some examples of that as well. Now, one that we get told a lot, and you see a lot in blogs, is disabling fsync. How many people know what that does? A few folks? So what this basically tells your database to do is, yeah, don't sync it. Do it whenever you want. Take it easy. But what that means in practice is, if it crashes, if that box crashes while you're in the middle of doing something, guess what? You have possible corruption at your database. And your database may come back up and it may look fine, and you'll have latent corruption. So this is one of the recommendations that we don't want you to do, right? Instead, what we want you to do is disable synchronous commit when you're doing data loading, and I'll show you why. And that basically tells the database, do it in a safe manner, but do it when you want to, and don't return, you're just basically not telling it to return to you and block on those things, but it's still all syncing to disk. Come on. Clicker. Okay. So I did a benchmark again where I went and ran a workload to do inserts into a database. So again, transactions per second is on the vertical axis, so bigger is better. And I started with 16 checkpoint segments, and that's in blue, and the 256 in purple. So when we have both of those things turned off, like you're doing f-syncing, you're doing synchronous commit, pretty much no difference. Now, we turn off f-sync, and this is why the recommendation existed for so many years to go do this. You get a dramatic improvement in performance, right? But guess what? If we just turn off synchronous commit, we actually get a better performance boost. But of course, the first time I showed this to someone said, well, what happens if you turn them both off? So of course, we tested that as well. And you see a small performance improvement over just turning synchronous commit off, but it's 4%. How many people think getting 4% faster data loading is worth the chance of corrupting your database? How many people's bosses think that's a good thing? That's not the conversation I ever want to have with my boss that, well, yeah, I got the data load done 4% faster, but we don't know if the data is really in there or not. So now, of course, the big win is just turning off synchronous commit. We got 100% improvement, right? More than 100%. So that's not typically how you load data. Normally you do it via copy or some bulk command. So I did a bulk load. This time it's time on the vertical axis, so shorter is better. Now notice the big difference here. The 256 checkpoint segments made a really large decrease, right? We haven't done anything else. All we've done is had more checkpoint segments. When we go turn off fsync, we don't see much of a change at all. And actually, even synchronous commit, you don't see much of a change. So depending on what you're doing here, changing different parameters is actually more important. We turn both off again, 3% difference. Again, not worth making much of a change. Even turning off synchronous commit in this point, still might get a little bit out of it, but it's probably not the biggest thing you could have done, right? increasing your checkpoint segments is more important. So talking about maintenance work memory, I wanted to show both that and checkpoint segments along with the fsync. So in this case, I'm turning synchronous commit off. I just said, fine, that's the best practice. We'll start with that. Fsync is on the one and off on the other. So we built the index. It took 29 minutes. Shorter time, better. So we start with, we go from the 16 meg maintenance work memory to a gig, right? Big, large increase. We get some nice improvement in the index performance in the build time, right? Saved us a few minutes. So that's much more important than turning fsync off. And if we go and add more checkpoint segments, we get another decrease. So you can see as we make these tunable changes, they're much more important than turning off fsync. And this is my general rule, as I always tell people, like, these are good starting points, but testing is really important because your mileage will vary, depends on what kind of system you're running on, how much memory, how much IOPS. One of the other things that's very interesting about Postgres is vacuuming after data load. How many people know that you have to vacuum after you load data? So most of you that have been running for a long time, you know this because it's something you learn. It's not intuitive that you would need to do that because most people think of vacuuming as being, hey, it's only when I update or delete a row that I need to vacuum it. But actually, you need to vacuum after you've inserted data. And I ran this test where I did a PG bench and I initialized my database, and then I basically ran a read-only workload on it. And what you see in the orange is my CPU, and in the green is my write IOPS. And what's strange is you're running a 100% read workload, and you're generating 5,000 write IOPS. And it's like, what's going on here? What's Postgres doing? What Postgres needs to do is it needs to clean out some stuff in those blocks. So it can do it when it vacuums, or it can do it the first time you touch that page. But of course, that causes everything to slow down. Even though you're just trying to read data, it's writing it out. So I stopped the test, I did a vacuum, and you can see my IOPS go up a lot because I'm writing out all those blocks. And then I reran the benchmark, and now I'm getting over twice the TPS because I'm not doing any writing. So analyzing and vacuuming after data loading, really important again. So how many people have had a transaction ID wraparound? If you've ever had one, you'll never forget it, will you? So this is super painful. You get 2 billion transactions in Postgres. I don't know why they picked that. I read the original paper, and it was, it's pretty funny because, at that time it probably sounded like a very big number. Nowadays it doesn't sound like a very big number at all, right? If you run out of the 2 billion transactions, basically at a million to go, it basically causes you to stop your database, go into single user mode, and one by one in serial vacuum each of the tables. You can imagine that is not a great experience. You can have your boss being like, when's the database coming back up? And you're like, I don't know, because it's just got to work its way serially through them. So you don't want that to happen. So you actually want to have to look at your vacuum parameters. Now, there's some really good talks from some of the Postgres core guys on this. I'm not going to go into a lot of detail because you could spend a whole hour talking about vacuum. But I will tell you that these are the parameters you really want to think about. You want to think about your scale factor, your vacuum thresholds, the number of workers you have, and really make sure that it's keeping up. And one of the things that's not obvious is that anything is a transaction, like doing a primary key violation, right? Even though you didn't change any data, will cause a transaction ID to increment. So we've had customers that basically were running through a large number of transaction IDs because they were hitting, key violations. And they were like, we're not doing that much. How did we run through 2 billion of these? You can do a lot of violations very quickly. So that's one of the things to really look at. One of the cool things we added around moving data was support for the Postgres FDW. So you can connect to another RDS instance. You can connect to something like Redshift. Now, your mileage may vary with Redshift because it's an older version of the front end for Postgres. It's an 8 version. But I wanted to show it here because it's kind of interesting. Or to an EC2 instance. So with the RDS super user, you have the privilege to go create the extension Postgres FDW. You do that, and you basically create a server, and you give it the URL of your instance. Now, I'm using the CNAME here of my Redshift instance. That works really well for both non-VPC, like classic instances, or private VPC. If your instance is publicly accessible, the target, you'll probably have to use the IP address because we have some kind of funny stuff going on with our DNS. It's something we're working on, but it's not something that works today. So that's just a heads up. It won't work if you try to use the CNAME. So, but once you've got that created, you can select from the tables and you can insert. So I've seen people do stuff where they're like, hey, look, I want to push a little bit of data to Redshift. That works fine. But the better use case is where folks are wiring in Redshift to get some of their data out of their analytics stuff and present it back to their like OLTP system, for example, or just to another RDS instance. One of the other things we added support for is the session replication role. I love this thing because it's not an actual role, but it's called a role. And this is used by a lot of the trigger-based replication tools like Picardo or Londiste. And to explain it, I did like this little animation where I have triggers that are basically cross-inserting into tables via like an FDW. And if you had these triggers set up, if you did this insert and you don't have the session replication role set, that insert is basically going to flow, hit the table, hit the trigger. It's going to flow around, it's going to hit the other trigger, and it would just keep going forever in that little loop, right? And so that role basically allows you to say, no, no, no. If it's replicated, do it once. Don't keep doing it, right? So, you know, mostly people don't use this a lot. It's mostly just used by the tool chain, but we do support that today. So let's talk a little bit about scale and availability and some of the questions and the discussions we've had with customers. So one of them I get a lot is, how should I set my shared buffers? How should I think about that? With something like Postgres that's been around for a long time, you get some historical data where people will say, well, no, you should never set it bigger than a gig, you know, and that was based on some stuff around 32-bit systems, right? So, you know, your mileage may vary on just reading, you know, the blogs of this because, you know, timeliness is actually important in these things because the new versions always make changes. So you want to leave enough room for the processes, and it depends. You might have 1,000, you might have 10,000, you might have 10. But you want to kind of reserve that much space. RDS out of the box, we do 1/4 of the total memory as shared buffers. So in this case, if we're talking about like an R38 extra large, 244 gig, basically you'll have a 62 gig shared buffer. I think I did that math correctly. And then the rest goes to Linux page cache. Now, how many people here have used another database engine that uses the Linux page cache? It's not common anymore. Most of them, like Oracle and other folks, just use a shared buffer. So this is a little different. When you select data in Postgres, the Postgres process basically goes and checks in the shared buffer to see if it's there. And if it's not there, it goes asks through the OS to get at the disk. If it's in the Linux page cache, it returns it. If not, it goes to like, you know, the storage, in this case EBS, and comes all the way back to the Postgres process. Now you can see that if obviously it's in the shared buffer, it has to do one less hop to go down to the Linux page cache. And that's going to cut into your efficiency, right? So what's the rule that you want to think about? Well, really, shared buffers, what we've seen, works really well if you can get it to be right around your working set size. Now, your working set size is essentially the common work data that you're going to have to touch, the indexes and the data, right? That your application is going to touch over a period. So to kind of show this again, I went and did a PG bench. It's on an R38 extra large. And the working set is 10% of the memory. So I basically constructed PG bench to have 24 gig of data. And on the vertical, I have transactions per second again. And I ran it for a whole bunch of different, 25 up to, 800 threads, right? Just to give you an idea of how this looks. So with the red line, on the bottom, we have the shared buffers sort of as a percentage of the memory of the box. So on the left, with 3 and 6, the working set, it doesn't fit in memory, right, in the shared buffers. On the right-hand side, it does. And what you'll notice, of course, is that you get a little bit of performance improvement. You get 5 to 6%. Now, one of the interesting things is, notice, though, after we go up from 13 to 25, we don't get any better performance, right? So setting it super large isn't going to help you. And there are some areas where Postgres has trouble managing the shared buffer, so you don't want to just make it ridiculously large. You really want to try to size it to your working set size. So the next thing is, well, okay, who runs their database with 24 gig of data on a 250 gig box? That's not that common, right? So I went and did the same test with a 50% of memory. So here we go, and we're doing the same thing with the red line showing the difference between in memory or outside of memory. So again, what we see is an even more dramatic improvement at higher thread counts when we're talking about 50% of the working set size. So 3% is on the lower 25 threads, and you get up to 20% on the 400 to 800 thread model. So This is a way to get some nice free, extra, run on your system by not spending any more money, but just tuning your shared buffers a bit. One of the other questions we get a lot from, Postgres folks, most of you have used wall-based replication for a long time, and you're very familiar with it, so you like that model. And I get a lot of questions of, well, how does that compare to multi-AZ? When would I use this instead of multi-AZ? Should they work together? What should I do? So I wanted to walk through that. So with multi-AZ, you start off typically with your database and your application in one availability zone. All of our regions have 2 or more availability zones today. These are just fake ones, AZ1, AZ2. You can see that we just start with that one AZ. Now, we really think you want to have replication into another availability zone. We also think that you want to have your application, in the other availability zone, just so that you'll have the most availability. Now, we use physical synchronous replication to do our multi-AZ. And physical, we want it to be fast. We want it to be able to keep up no matter how hard you push the box. The synchronous, though, is the real critical piece. Because what that means is that we can have confidence to fail you over to your secondary without data loss if there's an issue, right? With asynchronous replication, you have to make a choice. You're like, I might have all the data, I might not. Now, again, there's use cases for both scenarios, but as a service provider, it's hard for me to know whether you're running a gaming site where losing 5 seconds of data is okay, or you're a financial institution and losing 5 seconds means someone's getting fired. So the primary fails. What we do is we promote the secondary to a primary, but you'll notice, hey, the application's still pointing over at the other one. What we do is we have CNAMEs in front of all of our instances, and that's maintained by DNS, and that's how your application connects to RDS. So when we do the failover, we tell DNS, hey, we've moved, go tell the applications. So this whole process takes about 65 seconds for both the failover, the detection, and the update of the DNS. So that's what we see typically. Now, if you have a lot of database recovery, sometimes that'll take a little bit longer, but this, it's sort of in that range. If you are seeing longer recovery, it's usually that you don't have enough read IOPS to kind of do the recovery quickly. So that's one of the things that I like, and GP2 is very good at that. Now, the nice thing is whether just your database fails or there's a larger like networking or some kind of other event, you're set up to work no matter what. And of course, once this is all fixed, we go and rebuild that secondary automatically and get you back into a fully durable mode very quickly. So there's nothing to worry about. So that's what we think is sort of the primary means to get you high availability, especially in a general sense. Now, read replicas, though, can add a lot of functionality. These are just standard wall-based replicas. So here I'm showing multi-AZ, and let's add some read replicas. Now notice how they're being fed by the primary, and your application's talking to the database. So my example here is always I say, what if you had a blog site? Well, the guys that need to write blogs, they need to write to the primary, but all the readers of the blogs, they don't care. They're fine getting a read that's a second old, so you can point them at the read replicas, right? And the nice thing about this is, when you do something like a failover from a primary to a secondary on multi-AZ, there's that 65 seconds, right, where you're not going to be able to write. But if your readers can go and read from the replicas, then no one ever notices that your blog site's down, right? Just the one guy trying to write his new blog has to wait a couple, 65 seconds before he can write another blog entry. And then once that comes back up, everything's good. Now notice how the replication moves with it to the read replicas. You don't have to change anything. You don't have to do anything. That's all handled automatically. No work there. And this works really good if you have to do an upgrade on your primary database or any of your replicas, right, or modify them or do anything. Gives you a real high sense of read availability. Now this can also be used without multi-AZ if you're fine with taking the data loss and doing your own promotion. So let's talk about how that works. So here again I have that same sort of diagram, multi-AZ, applications talking to read replicas and to the primary, doing the synchronous replication. So let's say we want to go and promote this one in AZ3 because we don't have anybody talking to it. Now we might do this from a DR perspective. We might do this because we just want to spin off a copy. We do a promote call inside of RDS. This takes a few minutes to happen, and you get a new primary, so it looks just like your regular instances. Now, notice that we don't do any following. Like, none of the other read replicas move to become children of that primary. It's just that one instance that changes. And then you can connect an application to it. You can make it multi-AZ. You can turn backups on. You can modify it. You can do whatever you'd like. Now, of course, one of the main reasons to use read replica is scale, right? Is that, you have multi-AZ, that's great, but you can go add a lot of readers, and the nice thing is too, when you think about it, if you want to get even lower latency than you normally have, you can put your applications so they talk to the one in the same AZ, and that'll probably shave off like a half millisecond to a millisecond off of transaction times, which, for most people probably is not critical, but it is an option that you can do. So, replication works really well, and for those of you that have used it, the wall-based stuff, it's quite well built. We set up the streaming replication by default, but one of the things that can happen is the streaming replication can break for a number of reasons, just a network hiccup, whatever. And meanwhile, while it's broken, you're accumulating logs, right? You just continue to generate X logs. They keep happening on the primary. And this will just keep going on, until you get to, let's say, 99 logs. Now, Postgres at some point will start removing these based on what you set wall keep segments to. The good news is with RDS is we're backing those up because of the point in time. So we're constantly backing those up. So we can do a catch up even if the one is removed from the primary. And we can apply that to the replica and it, feed those through it to catch up. And then once streaming's back on, you're all good. But you really want to think about setting wall keep segments quite a bit higher because if you're doing that log shipping model, it's a very it's not as smooth as streaming. Your leg's going to go up and down as the logs are applied, right, as it goes file by file. So in general, you want to keep the streaming stuff running, so you want to set wall keep segments to a higher value than we typically default it to. And how do you know if you're streaming? You can look at pgstat replication view. You can see the state there, streaming. It's all good, right? One of the other things that folks have a lot of difficulty with is sort of the auto vacuum and replication. And I did this little animation to show that. So we have a row in this table, T1, called primary key A and foo. See it on both the source and the replica. Now, I'm just a person, I'm like, I'll just run this full table scan on this table for no apparent reason because I want to find this one piece of data, and I don't know how to use where clauses. So this is going to run for a very long time, right? No one's ever done this on a production database, I'm sure. But what happens if someone updates it on the primary, right? So we changed it to bar from foo. Well, in Postgres, that basically creates a new row. You keep the old row for MVCC. It's all good. And that will get replicated down to the replica. But it doesn't see it yet because, of snapshot isolation, right? It's all good. But then somebody runs a vacuum on the source. Well, guess what that does? That removes that old row. Great, didn't need it. But that gets replicated. Once it gets replicated, you get this nice error. How many people have had that error? A few people? Yeah. Not fun, because it kills your query. That query could have been running for 6 hours or 2 minutes, and now it's dead, and you got to restart it. So there's 4 parameters that basically you can use in Postgres to control this, and we'll walk through each one of those. So vacuum defer cleanup age is probably the least recommended one because you have to set it by the number of transactions you would like to keep. So let's say we're going along and we're updating this row over and over again. We're going to foo far, foo gar. So we get up here, and let's say on the replica, we need this row, T4. Well, if someone runs a vacuum, it'll go away, right? But if we set, let's say, the vacuum deferred cleanup age to 2, then it will keep those last 2. But the bad part is it's set across the whole database. You'd have to know how many transactions you want to keep. I mean, I don't know how many people can do that kind of math. I don't want to try, right? It's not time-based. So I don't find it very useful. Most people don't use that one. The next one that was really quite common and is still heavily used is max standby archive delay or max standby streaming delay. The one controls for streaming replication, obviously the one naming streaming delay, and the other is for archive. So let's say we set that to 30. What that's going to do is if there is a conflict, it will delay applying the streaming wall for 30 seconds until, at the end of 30 seconds, it'll apply it and it'll break your query. But if your query gets done in that 30 seconds, now you could set this to an hour if you wanted. But obviously, if you set it to an hour, your replica is going to lag by an hour when it hits a conflict, right? So you have to know that that's going to happen. Now, because we use both streaming and log apply, you want to set both of these, because if you don't, if we switch, your queries could die, right? The real caveat with this one is it's not per transaction. So if you start a session and it hits this, it doesn't mean that the next guy gets to run for 30 seconds. Because if he started 29 seconds in, he's going to run for a second before his query gets killed, possibly. So again, it's a little hard to model this in your head to get the right outcome. But it's still pretty useful, and it doesn't really impact the primary. And that's what a lot of people like about this one, is that there's, it just delays the replica a bit. The one I like a lot is hot standby feedback, because I think it's a little simpler to understand. So essentially what this does is it's on the replica, it's off by default, you just turn it on, and it's like it gives information back to the primary about what's going on the replica from a read perspective. So if you go run select star from T1 like I did, what it does is it makes it look like to the primary like it's running there. So that the vacuum process will say, oh, you're running a long-running query. I won't go and remove those rows. So it basically will stop auto-vacuuming from touching those rows while you're having a conflict. This is good and bad, right? You're going to get all your queries done. The bad part is you may be blocking your vacuum, right? You block your vacuum too much, you get transaction wraparound problems. So you do have to be careful. The other thing to remember is that if streaming replication breaks for some reason, and we do manual wall file apply, this would cause that to break again, right? That query would break because there's no feedback going because there's no streaming. So if you're going to use hot standby feedback, you still probably want to configure the other parameter as well around archive delay. So combinations, a lot of people use a lot of combinations in this. How do you see the conflicts? pgstat database conflicts. You'll see here I got one on this conflicting snapshot isolation where I did a vacuum basically on a table that I was running. So really helpful. One of the ones I like that we added from an informational perspective is pgstat statements. How many people use that on a regular basis? A few? It's super powerful. So it's an extension, but it's kind of a goofy extension because you have to load it as a shared library first. So you have to know that you need to do it. So by default, it's not loaded in RDS. So if you want to load it, you're going to create a custom parameter group, add the shared library, pgstat statement. It's the only thing that's allowed in the shared preload libraries option at the moment. Once you do that, you can go create this extension. And what it gives you is, pgstat activity tells you what's going on right now in your database. The nice thing about a pgstat statement, especially if you take you pull from it on a regular basis, is you can see what your statements are doing, how much effort they're basically taking to run, whether anything's changed, how much reading they're doing, how many rows, all good information. So I really recommend turning this on. It's something that we've talked about, maybe turning on as a default in newer versions. We haven't got there yet. It'd be great to get some feedback on that from folks. The other one that I'd like to talk about is burst mode. So I talked about this last year for anyone that's seen this. I've made some changes, but I think burst mode is actually one of the interesting things that we're doing in RDS and in EC2 in general that really changes the cost economics about doing some stuff with databases. So with the T2 family of instances, they basically allow you to burst. Now, anyone that used a T1 and has said, I'm never touching a burst model again, I understand. You got burnt. The T2s are much, much better. They really do work. So you start off with a base performance. If you're below that base performance, you're earning credits, and you get to spend them later by bursting. The nice thing is, for the T line, you actually get CloudWatch metrics that show you those, and I'll show you those, the credits and the usage graphs. On the storage side, EBS released GP2, their SSD-based storage. So this is very similar to PIOPS, but instead of getting a guarantee about an overall number and having to pick a number, you basically get 3 gigabytes, 3 IOs per gigabyte. So if you're not using those 3, they start going into a bucket that you get to spend later. Now, unfortunately, at the moment, there is no metric for this, so it makes it a little hard to kind of figure out. It's definitely something we've pushed EBS on to try to rectify. And with RDS today, you can burst to at least 3,000, if not higher, depending on your storage size. So to show this in action, I ran pgbench, and this is the CloudWatch metrics for this instance. So the green line is my CPU, and the orange line is my CPU credit balance. So as I'm running, it basically is using up credits because I'm pushing the box really hard, and then I get to that point where I exhaust the credits. You can see it gets down to 0, and my CPU drops, right? So you can monitor this, and you can see, hey, I'm spiking a little bit, but it's fine. I'm not going to use all my credits up, right? And if you are using all your credits up, maybe go to a bigger box, right? The cool thing is, we've just announced a new member of that family, the T2 large. It has more initial credits. It has a higher base performance, comes with more RAM, has bigger I/O bandwidth, but the big, really big one that I'm really happy about is it supports encryption at rest. So if you were in production using encryption at rest today, you had to be on an R3 or an M3. That's great, no problem. I probably need that big box anyway. But now I want to make a test copy of my database. Oh wait, I can't use a T because they didn't support encryption. I can't put those volumes on that box. So this is either EBS or RDS. So the nice thing is now this is supported as encryption at rest. So it's not the smallest box we have, but it definitely is a lot more cost effective than using an M or an R as a test instance. So I ran this benchmark last year. I updated it with some new results. I start off running, basically a workload, 100% read, 20 gig of data, and the data is bigger than the size of memory. So we're going to do some I/O. Transactions per second again on the vertical, and I ran it for 24 hours to kind of give you the full scope. I started with one of the older instance types, the M1 medium. So we still have a lot of people on these. They were our first instance types for a long time. And I ran it with the magnetic standard EBS storage option. So 200 gig of storage, costs 58 cents an hour. We get almost 2,000 transactions per second. Not bad. If we go to a modern one, an M3 medium, and we add provisioned IOPS, well, the interesting thing is it actually costs less because it's a newer instance class, and the price economics are better on them. And not only did we cost less, but we actually got a performance improvement by going to that. If we go up to a large, you see on this workload, we don't actually get a lot of benefit, but the cost economics, it's actually funny because the TPS, the dollar per TPS is exactly the same. It costs a little more, but I got a few more transactions per second out of it, so it's not a bad add. But let's go compare this now to the T line and to GP2. So the first thing I did was take a T2 medium with 200 gig of GP2. So that means I get basically 600 IOPS, right? Guaranteed 3,000 burst. Now notice this little bump here. So we start off running faster than any of the previous results because we're bursting in GP2. We're getting 3,000 IOPS. That's more than we bought on any of the other environments, right? But after 2 hours, we run out of GP2 credits, and we slow down dramatically, right? Now, hey, we're not getting a lot of TPS at the end, but also look at that cost. It's 10 cents an hour. It's very cost effective if you only needed to burst for a couple of hours a day, right? Way better than the 40 or 50 cents an hour. But the nice thing about GP2 and kind of the hidden secret is, guess what? You can just go buy more storage if you need more IOPS. You don't need to just use the storage you have. So I was like, let me go buy a terabyte. It's going to get some big storage, right? That gives me a guarantee of 3,000 IOPS, right? Plus the ability to burst above that. So now I'm getting 6,000 TPS, right, for the first 2 hours before I get throttled by my GP2 limits, right? I continue on for 17 hours to be faster than any of the other previous runs until I hit the limit of my credits on my T2, right? So I go down to being almost the same as the M3 medium at the end, but look at the price difference. We're 23 cents an hour versus 40, right? And you were able to burst higher earlier on than you were with the M3 medium. Really good stuff. And this is what I presented last year. Now the cool thing is, this is the result for the T2 large. So 12,000 transactions per second. Part of the reason is it has more I/O bandwidth. So we weren't actually able to go and burst all the way with GP2 on the medium because it just couldn't get enough I/O out of the box. The T2 large actually has the ability to go use more IOPS. Now you'll notice that it didn't run for as long because it used up its credits sooner, but got double the TPS, so that's pretty impressive. Now you'll notice that that red line runs out flatter for a much longer time, goes out to 21 hours. So even though we're doing more TPS, because we have more memory, so we're using less I/O, it has a higher amount of burst built into it, or its base credits are higher, so you can run for longer in burst. Now I will say this about this benchmark. This is what you would get if you ran for 48 hours, because for 24 hours these instances weren't doing anything. They were basically accumulating. So this would be, if you had this workload, let's say every 2 days or half of the amount of burst every day, because you have to accumulate the credits. I just did that to show because it makes it easier. But notice at the end here, 30 cents an hour, we're still faster than every other thing in this category, right? So we've improved our performance by, almost 50% for less money. So this really shows you how the burst mode stuff can really change. Now, you don't have to use GP2 with T2 or vice versa. I combine them to kind of make a larger point, but T2s on their own or GP2 instead of PIOPS really makes sense. And my rule of thumb is basically if you're probably on RDS and you need less than 10,000 provisioned IOPS, or 10,000 IOPS, probably use GP2. You're gonna save a lot of money. Your performance is going to be probably the same or possibly better because you have the ability to burst, which you don't have with. And it's only if you need way more IOPS or you really need the strict guarantees that PIOPS gives you around quality of service that are higher than GP2 is really the only reason to go to something like that. So that's I think a really key that now you can start using things in different ways. And if you have a burst kind of model for your application, this is super good stuff. So with that, I'm going to wrap up. Thank you very much.